Good afternoon, everyone. In the last class related to the amorphous systems, we had discussed about the estimation of glass transition temperature. We are now going to move over to the next topic, that is related to the stability of the amorphous form. We all know that the amorphous form is thermodynamically unstable form because it has a higher free energy as compared to the crystalline form. And that is the reason why it always has a tendency to convert back to the crystalline form upon storage. This is the energy diagram. Here is the amorphous drug and here is the crystalline drug, and this is the scale showing the arbitrary free energy units on this scale. As you can see, the amorphous drug has a higher free energy as compared to the crystalline drug, which has a lower free energy. And this is the difference between the free energy of the amorphous form and the crystalline form. Amorphous form, after crossing this energy barrier, what is also called as the activation energy barrier, will start converting to the crystalline form because crystalline form has the lower free energy. Nature always prefers systems to acquire the lower free energy state. Now this free energy barrier in fact is not that steep in the case of amorphous systems, and they are very quick to convert to the crystalline drug. That is why they are also called as the metastable state. There are two terms which are used. One is called as the metastable state and the other one is called as a unstable state. The difference between the two is with respect to the quantum of free energy barrier. When the free energy barrier is relatively high, as has been shown in this case, we will call that state as the metastable state. But if this free energy barrier is very less and the conversion takes place almost automatically, then the state is called as the unstable state. So depending upon the properties of the amorphous drug, it could either be metastable or it could be unstable. The unstable ones will have a very fast conversion from the amorphous form to the crystalline form. The factors that govern the stability of the amorphous form are given here. The first one is the glass transition temperature. The next one is the molecular mobility, then the fragility of the glass, heat capacity change at the glass transition temperature, and the molecular weight of the drug which has been converted into the amorphous form. We'll be discussing these points one by one. We have in fact already discussed about the glass transition temperature in our previous slides. So I'll just repeat that the glass transition temperature has a very important role to play in the physical stability of the glassy state. Suppose we have the storage temperature as the room temperature, which is about 25 degrees Celsius. If the glass transition temperature is close to the storage temperature, then the conversion of the glass to the crystalline form is going to be rather fast. But if the glass transition temperature is very high as compared to the storage temperature of 25, then the conversion of the glass to the crystalline form is going to be relatively slow. And there is a rule which is called as Tg plus 50K rule, which means if the Tg of the material is about 50 degrees higher than the storage temperature, then that glass is going to be relatively stable at that particular storage temperature. So this is the role of the glass transition temperature in the stability of the amorphous form. Rest of the parameters we are going to take up one by one. The role of molecular mobility in the conversion of the amorphous form to the crystalline form is very, very important, and we need to understand this concept in slightly more detail, because this is going to be useful when we are going to design the amorphous solid dispersions for pharmaceutical applications like increasing the aqueous solubility. Molecular mobility refers to various molecular motions that can take place in any solid, liquid, or gaseous state. Generally, the molecular mobility follows the order. The molecules in the gaseous state have the highest mobility, followed by the liquid state, followed by the supercooled liquid state, followed by the glassy state, and followed by the crystalline state, which means the crystals have the least molecular mobility, while the maximum molecular mobility is in the gaseous state. In terms of the solids, if we look at that from the perspective of the solids, so the glassy systems have more molecular mobility as compared to the crystalline form. And the reason for this is not very difficult to understand. In the crystalline form, the molecules are held together by the intermolecular interactions in the crystal lattice, which prevents their translational or diffusional motion, which means the molecules are not able to move from one point to another point. These are the different types of molecular motions that can exist in a system: vibrational, rotational, and translational. The translational motions are also called as the diffusional motions. Now we'll understand the molecular motions with specific reference to amorphous material, and we will discuss two scenarios. First, we will discuss the molecular motions that occur below the glass transition temperature, and then we will be discussing the molecular motions that occur above glass transition temperature. Remember, below the glass transition temperature, the material is in the glassy state, and above the glass transition temperature, the material is in the supercooled liquid state. So we'll first take up what are the types of molecular motion that occur below the Tg value. So molecules in the glassy state, like those in the crystal, primarily exhibit vibrational and rotational motions. So we are saying primarily, which means there are other motions also possible, but primarily they are vibrational and rotational motion, and neither of these leads to any change in the final locus of the molecule. As you know, vibrational motions occur to and fro with the same locus being maintained, whereas the rotational motions would also not involve change in the locus of the molecule. Locus of the molecule means that suppose if your molecule is at this point, if it moves to a point here, then this would be called as change in the locus. But if the molecule remains at a particular point and shows certain motions, then we are going to say that these motions are not causing any change in the locus of the molecule. However, below the Tg, molecules also exhibit translational motions or the diffusional motions, but they occur as slow motions, means they are very slow in nature and they occur over long time scales, which means the diffusional motions, although they occur below the Tg, but they occur very slowly. They are not occurring at a fast pace. So these motions, whatever occur below Tg, are independent local motions. What we mean by independent local motions is that they keep on occurring in individual molecules, and the molecules are not going to be associated with their neighboring molecules for these motions. They will keep on occurring independently in one molecule. And these independent local motions have been given certain terminologies, and they are also called as secondary or beta or Johari-Goldstein relaxations. So these are the three terminologies which are used for the independent local motions that occur below the glass transition temperature. I'll repeat their names: secondary relaxations, beta relaxation, or Johari-Goldstein relaxation. These are in fact the names of two scientists who have worked a lot in the area of amorphous systems. And this scientist Johari in fact is an Indian scientist who works in US on the amorphous systems. So this was with respect to the motions that occur below Tg. So we'll try to summarize these, that below the Tg, the main motions that are occurring are vibrational and rotational in nature, but there are some translational motions also occurring, but they occur at a very slow pace. And these motions that occur below Tg are independent local motions and are called as secondary, beta, or Johari-Goldstein relaxations. Now we'll move over to the molecular motion that occur above the glass transition temperature. And remember, above the Tg, the material is now into the supercooled liquid state. So molecules in the supercooled liquid region, that is above the Tg, exhibit translational, also called as diffusional motions at lower time scales, which means there are high motions or they are occurring at a higher speed as compared to what occurs at below Tg, which leads to change in the locus of a given molecule, which means the molecule from here is going to move to another new locus. That is why we call it diffusional motion. This change is due to the critical free volume being available and is seen as a step change in heat capacity of the material at glass transition temperature. What it means in simple terminology is that at the Tg there is a change in the free volume of the system, and since now greater free volume is available above the Tg, so the molecules are free to move in the translational manner. In other words, they show diffusional motions at a higher frequency now. So these motions that occur above Tg, they are cooperative in nature and they are diffusional global motions. Now what we mean by this term cooperative diffusional global motions is that these motions are not occurring in the individual molecules, rather they occur in the group of molecules, which means the single molecule is cooperating with the neighboring molecules for these motions, and all of them move together rather than individually moving from one place to another or individually showing the motions. So that is why we call them cooperative diffusional global motions, and they are also called as primary or alpha relaxations. So if we try to summarize the molecular motions above the Tg, the important points to consider here are that the molecules here will also show vibrational and rotational motions, but they also show a great tendency towards the diffusional motions, or what we also call as the translational motions. And these translational motions occur because there is a change in the free volume. There is an increase in the free volume available, and because of that the molecules are now free to move from one place to another place. And these motions are cooperative in nature, which means it does not occur in individual molecules, rather it occurs in group of molecules. The entire system now behaves as one unit. So they are called as cooperative diffusional global motions because they occur throughout the system, as compared to these motions which occur only in the local domains. These are occurring globally, and they are also called as the primary or alpha relaxations. Now this is an interesting diagram which we are going to look at this particular tree. So this tree depicts the amorphous system. So there are the branches of the tree, and on those branches there are certain leaves which are there. So what we'll see that in the case of the secondary relaxation or beta and local motion, which are also called as Johari-Goldstein relaxation, remember these occur below the Tg. So only the leaves of the tree will be vibrating at their place. There will not be no movement in the branches because these motions are local motions. So these are intra and intermolecular motions known as the local mobility. They are non-cooperative in nature because they occur independently in the molecules. The activation energy value is much lower for these motions as compared to the alpha relaxation motions, and they are universally present in both rigid and non-rigid organic small molecule classes. And these motions ultimately will give rise to the cooperative alpha relaxations. In other words, beta relaxation is the starting point for the alpha relaxation subsequently. Now see carefully, I am going to click this slide and you will you will see some motions occurring in these green colored leaves of the tree. So you can see only the leaves are moving. The branches are static. This is what we mean by local motions, and they are occurring only in the local domains. They are not occurring throughout the system. That is why we call them local motions. Now, in comparison to this, the primary alpha relaxations, they involve the entire branches as well as the leaves. So you can see the branches are moving as well as the leaves are moving. So these molecular motions are observed above the TG and they are known as global mobility because the entire tree was in fact moving when we saw the animation. They are directly related to the physicochemical stability of an amorphous phase, and they happen due to thermal effects which reflect an increase in kinetic energy of molecules above Tg, resulting in increased free volume of the system. And because of this increased free volume of the system, the diffusional motions are able to occur at a greater frequency. Molecular mobility is best expressed in terms of what we call as relaxation time, which is denoted by this abbreviation small t and s in the subscript. Structural relaxation time is defined as the time taken by the molecule to diffuse from the center of its vibration to another center across the intermolecular distance. And if you recollect, this particular relaxation time is going to be very high in the material when it is below the glass transition temperature, and this is going to be a small volume, it is going to be a small value when the material is above the glass transition temperature. There are various methods that are available to measure the relaxation times, and one of them is DSC, dynamic mechanical thermal analysis can also be used, dielectric relaxation spectroscopy, enthalpy and volumetric relaxation, and solid state NMR. All these techniques can be used for measuring the relaxation times. We are not going to get into the details of these techniques because they are beyond the scope of the current subject, but they are used in the lab at NIPER as well for characterization of the molecular mobility in the amorphous systems. Now, what are the consequences of molecular mobility? So, molecular mobility leads to what is called as relaxation of the material. So amorphous materials can age or relax over time. Upon relaxation, there is an increase in the density of the material and the free volume decreases. Let us try to understand this term relaxation using some day-to-day example. Whenever there is entrapment of higher energy into any system, the system tends to lose that higher energy to the environment, and by this way it relaxes. If you remember, when we do certain exercises for relaxation, what we are trying to do in our body is that whatever is the tension that has built in the form of higher energy in our body is dissipated to the environment and our body relaxes. So the same concept applies to other systems as well. Whenever there is higher energy trapped in a particular system, it will tend to lose that higher energy into the environment, and by this process it will get relaxed. So one of the ways by which the amorphous systems relax is by losing the excess enthalpy which is there in the amorphous form. So this is the unaged amorphous matrix or amorphous sample. So these are the molecules shown by these circles, and upon enthalpy relaxation, which is nothing but losing the excess enthalpy to the environment, the material becomes aged, and you can see the molecules have now come closer to one another. So there is an increase in the density of the sample, and then there is a decrease in the free volume. So how we can look at the decrease in the free volume? These white spaces indicate the free volume, and these are the places which are available for the motion of the molecules, especially the diffusional motions. In this case, you will see these white spaces have drastically reduced, so there is a decrease in the free volume. So this phenomena is called as the aging of the glass, and from an unaged sample to the aged sample, there are changes in the density and the free volume. Aged materials show decreased physical and chemical reactivity as compared to the unaged materials, which means that the unaged glass is more reactive in terms of physical and chemical reactivity. And this is shown here. So the unaged amorphous matrix, it relaxes and goes to what we call as the aged sample, which was shown in the previous slide as well. But if we expose this sample to water, so exposure to water can reverse the aging of an amorphous material and make it more reactive again. So this is the water vapor absorption. So water is being picked up by this aged sample like this, and there is expansion of the condensed matrix because of the ingress of moisture into the system. Remember, water is a very strong plasticizer, and it will lead to the reduction in the glass transition temperature of the system as well. Now, if you dry this sample at a low temperature, which is far from the TG, it will lose the moisture and you will regain the same structure with which you had started. So the water molecules which are shown here by the small black colored circles have been removed during this phenomena of drying, and there is reversal of physical aging of the glass that has happened in this particular step. The next aspect that is related to the stability of the glass is its fragility. The rate at which the viscosity or the structural relaxation time of amorphous solids change as a function of temperature can be quite different with different types of solids. So the different glasses or glass samples or amorphous samples of different materials will behave very differently in terms of the rate at which their viscosity changes as a function of temperature. And this concept was given by a scientist called as Engel, and he had suggested what we now call as Engel plots. So in the Engel plot, if it varies exponential with temperature, then it is called a strong liquid, and if it varies non-exponentially, then it is called a fragile liquid. And then there is a m value that can be calculated, and if the m value is less than 25, then the amorphous system is called as a strong liquid, and if the m value is greater than 75, then it is called as a fragile liquid. By liquid, we are referring to the supercooled liquid state. We do not mean that the sample is actually a liquid. So this liquid refers to the supercooled liquid state. This is one example of the angel plot, and on the x-axis you have the glass transition temperature divided by the temperature, and on this axis you have the logarithm of the viscosity. So in the strong glasses there is a exponential decrease, and silicon dioxide is one example. So there is a straight line that you get in this particular graph, and these are called as strong liquids. Whereas in the case of this particular reagent called as OTP or the glycerol, the exponential behavior is not maintained, and it shows a non-exponential change in the viscosity of the system based on the temperature of the system. So these are called as fragile liquid. Just for your information, all the pharmaceutical glasses or all the amorphous pharmaceuticals usually behave somewhere around this behavior, and they are fragile liquids. So they are not strong liquids, they are rather fragile liquids. So SiO2 represents a strong liquid while OTP represents a fragile liquid. And this is the equation that is used to calculate the M value, which we were referring here. So the fragility can tell you the stability of the system. So if something is a strong glass, then it is going to be relatively more stable, while if it is a fragile glass, it is going to be less stable. Another interesting aspect that is related to the fragility is that if you want to use temperature as a means of stabilizing the amorphous form, then for the fragile liquids, the change in the physical stability is going to be significant as you change the temperature of storage. Whereas in the case of the strong glasses, this change is going to be very moderate, which means if you decrease the temperature from a value x to a lower value, the increase in the physical stability of the fragile glasses is going to be more as compared to that for the strong glasses. So if you have a fragile system, then the storage temperature can be effectively used as a strategy to improve the physical stability of the amorphous system. The next concept related to the stability of the amorphous form is the heat capacity change at the glass transition temperature. And this is an experimentally accessible thermodynamic quantity for characterization of the amorphous state. In fact, in the DSC, there is an option to measure the heat capacity change. So you have to calibrate your equipment of the DSC for measuring the specific heat of the system. So the large change in heat capacity is associated with the fragile or weak intermolecular bonding or behavior of the glasses. So if your amorphous system is a weak or a fragile glass, then the change in the specific heat at glass transition temperature is going to be higher as compared to a system which is a strong glass. So here it is shown as a case study or as an example. So this red line is for the crystalline material and this blue line is for the amorphous system. So on this axis you have the temperature and on this axis you have the heat capacity. So as you are heating the crystalline sample or the amorphous sample, the crystalline sample does not show much change in the heat capacity with increase in the temperature until it reaches its melting point. Whereas the glassy material will show a step change in heat capacity at the glass transition temperature. And this is the delta Cp or the heat capacity change that occurs at the TG. So this change is going to be higher for the fragile glasses, whereas this change is going to be lower. So you may only see this much change in delta Cp for the strong glasses. So that is the difference between these two behaviors with respect to a fragile glass and a strong glass. Now there is another term which is called as the configurational Cp or configurational specific heat. So this is the difference between the specific heat of the crystalline material and that of the amorphous material. So this difference is called as the configurational heat capacity of the glass. Then there is also a correlationship between the stability of the amorphous form and the molecular weight, and it has been shown by a couple of very good publications that the drugs that have higher molecular weight, especially greater than 300 Daltons, have the higher tendency to form glass than those which have lower molecular weight. So drugs that have a molecular weight of greater than 300 will have a greater glass forming ability, which means if you melt them and then you cool them, there will be a greater tendency or a greater possibility of generation of the amorphous form. Larger molecular weight and complex molecular structure of high molecular weight compounds requires larger number of conformations and configurations to find an ordered structure during the cooling or the solidification, and this is the reason because of which they show better glass forming ability. Time available to find a configuration that will produce an ordered crystalline unit during solidification would be more in the case of complex and high molecular compound. Till date, molecular weight is the only robust parameter to predict the glass forming ability of a particular material. So the materials that have a good glass forming ability are also shown to have a better stability of the glass that has been formed. So in brief, if we want to put it in a very simple way, APIs that have low molecular weight will show poor glass forming ability, and the stability of their glass, if formed, is going to be poor. Whereas APIs that have relatively higher molecular weights will easily form an amorphous state, and that amorphous state is also going to have relatively better stability. Now, when we say relatively better stability, it does not mean that it will have a stability higher than the crystalline form. We are only talking in relation to the glasses for the small molecular weight compounds. So we are going to stop here for this particular class, and if you have any questions, as usual, post them on the WhatsApp group. In the next class, we are going to take up the generation of the amorphous form. Thank you very much for your attention, and I look forward to your questions on the WhatsApp group.